So what we're going to be doing today, we're going to pick up what we left off. We're just going to talk about like first order circuits. And then we're going to learn about like how to solve the differential equation associated with that circuit to basically get voltage across the capacitor or current through the inductor, right? The idea was that like we learned about like those storage elements, and we said like the relationship between I and V is basically through like these formulas that you can see on the board, right? If I have a resistor, relationship is linear, V equals Ri. If I have like a capacitor, the relationship is still linear, but it's through a derivative. And the same thing for the inductor, right? So we talked about these things before. And we define a first order circuit to be a circuit that has as many as resistors we want it, as many as sources, dependent or independent sources as we want it, but we only have one storage element, right? We could have like 2, 3 of them, but as long as we can actually simplify it down into like one storage element, we call that circuit a first order circuit. And the reason we called it a first order circuit was just because we ended up getting a first order differential equation, right? So let me quickly remind you of things that we talked about. Reminder. A first order circuit is a circuit with only one storage element. It could be either like a capacitor or an inductor, but there is only like one of them. And the reason that we called it a first order circuit was just because we ended up solving a first order differential equation. So we need to solve a first order differential equation. And we said, since voltage across the capacitor was the continuous variable, and current through the inductor was, again, a continuous variable, we're going to try to write down our differential equation in terms of like these two variables, right? Again, we can write a differential equation in terms of any variable in the circuit that we have, but we cannot be sure if they're actually continuous or not. Therefore, it would be hard for us to find the initial conditions, right? So we said we try to write down differential equations in terms of voltage across a capacitor or current through an inductor, right? And the reason was because these two variables are continuous variables. So these are continuous variables, right? We also talked about like the most general RC and RL circuits that we could possibly get. So if we have first order RL circuit, we said this is the most general RL circuit that we can get. This is IS of t. This is R. This is IL of t. And voltage across it is VL of t. And the reason like this was the most general way of looking at any RL circuit is that we can always like think of our inductor as the load and the rest of the circuit as the black box. And we could find the Thevenin or Norton equivalent circuit. In this case, it's a Norton equivalent. Therefore, this R is basically our Thevenin, right? So this is the most general RL circuit that we can possibly get. And by writing a KCL at this top node, writing a KCL at top node, we ended up getting this differential equation. DIL dt plus R over L ILT equals R over L IS of t. Right? And as you can see, I rewrote a differential equation in terms of current through the inductor, which is a continuous variable. Right? If I call this A, some constant A, and if I call this some function f of t, as you can see, this is the first order differential equation with coefficient A and some force function f of t, which we talked about it, and we said it's always due to the sources that we have. And as you can see, this f of t, which is a force function, is a function of your input source. Right? We also said like the most general way of looking at a first order RC circuit is by looking at this circuit. Right? And again, we said if you look at that capacitor, we can think of it as our load, and the rest of the circuit, whatever that is, could be thought of as my black box, and I can simplify it down using the Thevenin equivalent to this circuit. So that's why this is the most general circuit that we can get. But we can think of this R again as our Thevenin, right? And just by writing a KVL, for the loop, we can get this differential equation. dVc dt plus 1 over RC Vc of t equals 1 over RC Vs of t. And again, if I call this an A, call this f of t. Again, this is a first order differential equation with the force function 1 over RC Vs of t, which is always due to the source that we have. Right? We talked about these things before. We basically derived all these equations. If you don't remember, you can go back to our notes and check it out. But we derived it, right? Just by writing a KCL at this top node or a KVL in this, right? But the important part was, if I have an inductor, I had to write the differential equation in terms of current through the inductor, which is what we did over here. And if we have a capacitor, we need to write the differential equation in terms of voltage across the capacitor, which is exactly like what we did over here. And that was due to the fact that these two elements, these two variables, are continuous variables. But nonetheless, we're going to have to solve a differential equation that looks like this. dx dt plus some constant xt equals f of t. Right? So we're going to have to solve a differential equation that looks like this. If I have a circuit with an inductor, this x is IL. If I have a circuit that has a capacitor, this x is Vc. Right? Is that clear what's happening so far? Yes? So let's try to solve this differential equation. So the question is how to solve a first order differential equation. Let's just call it dx dt plus axt equals f of t. The very first thing that we talked about is that this differential equation has infinite solutions. So to make that solution unique, we're going to have some initial conditions, right? But let's table that for a second. Now let's just talk about the solution in general. The solution of this differential equation, always has two parts. let's just call it x of t, which is the solution. It is one part that is due to this force function that we have over here, which we call it the particular solution. This is the particular solution, which is due to f of t. And we have some complementary solution, which is due to the homogeneous differential equation. So we have the complementary solution, which is due to the homogeneous differential equation. And we know the homogeneous differential equation means when f of t is 0, right? So this is the homogeneous differential equation, right? For the complementary part, it's the easy part, right? We can always find like the integrator and just multiply it to make it a complete, derivative, and then integrate both sides, or we can look at the characteristic function of like this, which is lambda plus a equals 0. And we know the solution is e to the power of lambda t, right? So that's not the very hard part. The hard part is always the particular solution, because there is not a unique way to solve for the particular solution. So the way that you should be approaching it is always by guessing. You have to guess what that function is. And guessing is always difficult, right? So the good news here is the types of f of t that we're dealing with in this class are very simple. F of t in this class is either constant or a sine wave. So in this class, f of t is either constant or sine wave. Why is it a good news? Because if f of t is constant, the function I'm guessing is also a constant, right? And if f of t is a sine wave, the function I'm guessing is still a sine wave. It has different coefficients, but it's still a sine wave. And since I know the solution, the particular solution, is also the solution for this differential equation, I can always plug it in here, and I know it satisfies that equation, so I can find those things, right? For now, let's only focus on the constant part. Okay? So let's assume f of t is constant. Circuit-wise, what does it mean? If f of t constant, what it means is that the force function is constant. And if you recall, I just said force function is always due to the sources that we have. If f of t is constant, what it means is that all the sources that we have must be constant, right? So if I end up getting a differential equation with f of t as a constant, I'm expecting the circuit to only have constant sources, right? But let's go back and think about it mathematically and see how we can solve a differential equation with the force function a constant, right? So our idea here is that, so case 1, assume f of t is constant. Let's just call that constant c. And the goal is solve dx dt plus axt equals f of t, which is this, right? Again, I know the solution for this differential equation as the particular solution plus the complementary solution. The particular solution is due to the constant force that I have here. So what I'm assuming is that this particular solution is also constant. I don't know that constant, but I know it's a constant. So let's just assume to find xp of t, we know xp of t must be some constant k1, right? I don't know k1, right? But I know it must be constant. X particular solution is also a solution of this differential equation. So it should satisfy the differential equation, right? Therefore, I know the xp of t dt plus a xp of t is the constant c. If xp is constant k1, what is the derivative of it? It's 0, right? So I have 0 plus a times k1 equals c. Therefore, k1 is c over a. Right? So I found the constant. How about the particular solution? How about the complementary solution? Remember, the complementary solution is the solution to the homogeneous differential equation. So to find complementary solution, we have to solve this. Right? But as I just mentioned, I can find a characteristic function here, which is lambda plus a equals 0, right? So we know the solution is e to the power of minus lambda t, basically like minus a t, right? So x complementary t is some constant k2 e to the power of minus t times a, right? There's an a here. Right? We can write also this as k2 e to the power of minus t over tau, where tau is 1 over a. Right? There is no mathematical reason for doing this. But since we're not just doing mathematics and we're doing circuits, there is actually like a physical intuition behind this tau. So let me quickly write down this complementary solution. So we know x c of t is some k2 e to the power of minus at, which we wrote it as k2 e to the power of minus t over tau. We call this tau, which is 1 over a time constant. Which what it means is that it's basically the amount of the time that it takes for a capacitor or inductor to fully charge or discharge. That's a physical intuition behind this tau, and that's the reason we're writing it that way. So tau means the amount of time it takes for a capacitor or inductor to fully charge or discharge. Right? So if I go back to the equation that I had for the RL circuit, if I compare this to this differential equation that I have over here, what is my time constant? The time constant is 1 over a, right? Therefore, it is L over R, right? Everybody see it? So for an RL circuit, tau is L over R. How about for an RC circuit? What is the tau for RC circuit? That's RC, right? It's 1 over A, which is RC. Let's understand this thing a little better. Remember, this tau is representing the amount of time it takes for the capacitor or inductor to fully charge or discharge. And if the tau is bigger, it means it takes longer time, right? What happens if I have an RL circuit and R becomes smaller? What it means is that this tau becomes bigger. And if the R becomes bigger, it means it takes longer time for the inductor to fully charge or discharge. I can say the same thing for this RC circuit. If R is bigger, what it means is that tau is bigger. If tau is larger, what it means is that it takes longer time for an RC circuit to fully charge or discharge, right? So I have basically this relationship. R bigger, tau bigger. R smaller, tau bigger, right? But like that's basically like the intuition behind it. That's the main reason that we're writing it in terms of like tau. So to put it all together, this is what we have. We have this differential equation. And this f of t is constant. We know the solution for this differential equation is x of t, which has two portions, xp of t plus xc of t, which we know is k1 plus k2 e to the power of minus t over tau, right? And our job is to find k1 and k2. We already found k1, right, which is c over a, but we haven't talked about this k2, right? We got to be able to find that as well, right? So how to find k1 and k2? Well, like I said, we already know like k1. K1 is c over a, right? But let's look at it like from another angle. What happens if I find the value of x of t when t approaches infinity? What happens? Basically, what is this? Remember, this is x of t, right? If t approaches infinity, this term goes to 0. Therefore, this limit is nothing but k1, right? Which we already know it's c over a, right? How about if I look at x at time 0? What is that? If I put t equals 0, what is e to the power of 0? That's 1. So I have k1 plus k2 equals x at time 0. Right? So look what just happened. If I tell you exactly like how it works at infinity, and if I tell you exactly like how it works at t equals 0, you know exactly like what this equation is. So you have a unique solution as long as I give you the initial condition at 0 and infinity. Keep that in mind. There is nothing special about this 0. I can literally compute it at any time I want, right? The reason we're choosing like 0 is just because it makes this term go to 1. But if I tell you, like, for example, time 1, your initial condition, basically x at time 1, is some number. You know k1 plus k2 times e to the power of minus 1 over tau is that number, right? So there's nothing special about this 0. This 0 makes things a little like easier. That's why we choose 0, right? But if I give you any time t, you just need to like plug it in here, right? And you know the exact value for that time t, and you have like one equation, right? And if you look at it at infinity as well, you have two equations, two unknown, you can find k1 and k2. And as soon as you find k1 and k2, you have the unique solution to this differential equation. So given initial conditions, we can compute the unique solution of this differential equation by finding k1 and k2. Right? Does that make sense what we're doing? So let's go back to the circuit. So far, we just solved the differential equation. But remember, like in circuits, there is a meaning to this x of t. This x of t is either voltage across a capacitor or a current through an inductor, right? So there is a meaning to this x of t, and therefore there is a meaning to these initial conditions. Let's see like what it means. So going back to circuits, 1. X of t is either voltage across a capacitor, Vc of t, or it's a current through an inductor, IL of t. Because of that, we can find initial conditions given capacitor and inductor. But how? At time infinity, remember, like the times that we're interested in is time infinity and some time, like for example, 0. At time infinity, what's happening is that everything is in the steady state condition, right? What happens to a capacitor if we're in a steady state condition? It means voltage across the capacitor is constant. And what happens to the current through it? Current becomes 0. And if the current through it is 0, what it means is that the capacitor is nothing but an open circuit. How about an inductor? I know at time infinity, I'm in a steady state condition, so everything is constant, right? Therefore, I through it is constant. What is the voltage across the capacitor, an inductor, if current through it is constant? Voltage is 0. Therefore, what it means is that I can replace my inductor by a wire. What's very, very important here is that when I'm talking about like open circuit across a capacitor, What it means is that current through it is 0 does not mean voltage across it is 0. And same goes for the inductor, right? When I'm talking about like short circuit, what it means is that voltage is 0. It doesn't mean that current through it is 0. So at time infinity, we're in steady state condition, which means if I have a capacitor, that becomes open circuit. If I have an inductor, that becomes a short circuit, right? How about at time 0? Well, to be able to find the initial condition at time 0, we're going to have to use the continuity of voltage across the capacitor or current through the inductor. So to find x at time 0, we use continuity condition for Vc at time 0 negative, which is the same as Vc at time 0 plus, or IL at time 0 negative is the same as IL at time 0 plus. Which basically means like I have x0 plus is the same as x0 negative, right? X is either like Vc or IL, right? And if I know this, what I'm claiming is that I know exactly like what K1 and K2 are, right? Because remember, given x at 0 and xt when t goes to infinity, we know xt is k1 plus k2 e to the minus t over tau. Therefore, limit of xt when t goes to infinity is k1, and x at 0 is k1 plus k2, right? So if I know this, and I know this, I can find k1 and k2, right? We can find k1 and k2, right? So we can apply this to any circuit, right? So let's just see how. Let's just have like a recipe to follow through and solve for voltage across the capacitor or current through the inductor. So differential equation strategy to solve a first order circuit. Right? The first step is to write down the differential equation. But we're not going to write down the differential equation for all the variables or any variables. We're going to narrow it down to voltage across the capacitor or current through the inductor, because these are the variables that we are sure are continuous. So the first step is to write down differential equation for Vc of t or IL of t. How do we do this? We're doing it using like KVL, KCL, Thevenin equivalent, Norton equivalent, all those like methods that we learned. So doing this by KVL, KCL, Thevenin, Norton, or any method, right? Second step is to find the steady state conditions. Remember, the steady state conditions could tell us exactly what K1 was, right? So we need to find VC at infinity or IL at infinity, right? And we know exactly how to do it. We just need to like remove the capacitor and leave it open and find voltage across it. We know current through an inductor is constant. Therefore, we need to replace it by a wire. And that's how we get like either of these, right? Remember, by doing this, we only have like one of those constants. We need to like get another constant, which is our K2. To be able to do that, we need to use the initial condition at time 0. Again, remember that time 0, there's nothing special about it. It just made our life a little easier, right? So use the initial condition, either VC at time 0 negative, the same as VC at time 0 plus, or IL at time 0 negative, the same as IL at time 0 plus. And this gives us K1 plus K2. Remember, this one over here would give us K1, right? And therefore, we can find K2 here. And if I find K2, I know VCFT or ILFT, right? Because we know exactly what the solution is. The solution is K1 plus K2 e to the power of minus t over tau, right? Last step is to solve for unknown in the circuit. If the unknown in the circuit is voltage across the capacitor or current through the inductor, we're done in step 3. But if it's something else, we need to compute that. Okay? Any questions about these 4 steps before I do an example and walk you through all these steps? Is that clear what we're doing? The idea is that we're going to try to solve a differential equation. But this differential equation is not a regular differential equation that you have like in your math classes. There is a meaning to this differential equation. And we're going to have to use that meaning to be able to find the initial conditions, right? So let's do an example. Let's just say I'm given this circuit. Hundred microfarad. And I have a 3K resistor here. Let's just call this IFT. And let's just say I have a switch here, which is at position 1. For a long time, then it can go to like position 2 right at time 0. So the switch has been in position 1 for a long time. At time t equals 0, the switch moves to position 2 and stays there. The question is, find IT for time greater than 0. Right? So I have a circuit that looks like this. I know for all negative times, we're in position 1, which means this portion of the circuit does not exist, right? But as soon as I hit time 0, the switch moves from position 1 to position 2, which means this portion of the circuit does not exist. For all times that are greater than 0, this portion of the circuit does not exist, right? And the idea is, what is this IT, right? So let's go through our steps. The first step, step 1, we have to write down a differential equation. But what are we trying to write the differential equation for? Can we write a differential equation for this I of t? Well, obviously we can, but it's not useful because we don't know if that IT is continuous or not. So we cannot use any of the initial conditions that we talked about for IT. What we do know, though, is voltage across that capacitor is indeed continuous. So I can write a differential equation that's representing that voltage. So for time greater than 0, what does my circuit look like? Well, again, at time 0, the switch moves to position 2. Therefore, this portion of the circuit is gone. Right? You see why it's gone? Because it's in parallel with the wire. Right? So it's gone. So my circuit would look like this. Actually, it's not even like in parallel with this. It's going to be open here, so there's going to be nothing over there. Right? So it would look like this. Could not be in parallel with the wire. Do you agree this is my circuit for time greater than 0? Remember, at time greater than 0, I'm in position 2, which means this is open, right? And if this is open, it means this portion of the circuit is gone, right? 12 cannot be in parallel with the wire, right? Because voltage across the wire is 0, right? So it cannot be. So this is my circuit for time greater than 0. You all with me? Everybody see it? But look, do you agree if I call this a ground, this node over here is VCFT? Do you agree with that? Right? So if I write a KCL at this top node, what do I have? Let's just call this I1, this I2, and this I3. I have I1 plus I2 plus I3 equals 0. What is I1? I1 is VCFT divided by 6K. Right? You see it? So that is VCFT divided by 6K. What is I2? What is I2? I2 is current through this capacitor. What is the relationship between I and V? I equals C dV dt. Right? So it is 100 microfarad times dVc dt. Right? What is I3? I3 is Vc of t divided by 3K. And that should be 0. Right? Now I want the leading coefficient of this differential equation to be 1 because I want it to look like the equations that we had before. So I'm going to divide everything by this 100 microfarad. And I basically put together these two terms. So if I do that, I have dVc dt plus 1 over 100 microfarad times 1 over 6K plus 1 over 3K times Vc of t, and that must be 0. If you simplify that, this is a 5. right? You can just simplify it. It's not all those like numbers, and you can just like multiply them. So what you get is dvc dt plus 5 times vc, that equals to 0. Right? What is vc of t then? vc of t is some k1 plus k2 e to the power of minus t over tau. Right? What is tau over here? Tau is 1 over a, which is 1 over 5. Right? Therefore, it is k1 plus k2 e to the power of minus 5t. Right? All we have to do is to find k1 and k2. Right? If you look at this differential equation, the force that I have over here is 0. Right? So I can argue this k1 must be 0. Right? Because there's nothing going on. But let's just see how. Remember, like, if we had that constant, the constant was c over a. C is 0, so it's 0. But let's just actually like look at it from like a circuit perspective. This is the differential equation that we have. We know this is the solution for it. All we have to do is to find k1 and k2. Remember, to find k1, we need to look at the steady state condition, basically at time infinity. So at time infinity, so step 2, steady state condition. Remember, this is my circuit at time infinity as well, right? Infinity is like greater than 0. So this is still like my circuit. But if I look at this circuit, this capacitor is like fully depleted. It's fully like discharged, right? What happens to it if it's like fully discharged? We're in a steady state condition, therefore I have to open it. So what I'm going to have is that I have a 6K. This is VC infinity. And that's a 3K. What is VC infinity over here? What is it? There's no source in this circuit. So what is VC infinity? That is 0. Therefore, K1 must be 0. Which confirms our intuition, right? Because there is no force, there shouldn't be any K1, right? Down one constant, we got to find another one. We got to find K2. So step 3, find VC at time 0 plus, which we know that's K1 plus K2, right? But remember, at time 0 plus, I don't really know how the circuit behaves, right? I know it follows this equation, but I don't really know how to solve that equation, right? The good news is we know VC 0 plus is the exact same as VC at 0 negative. So what happens at like 0 negative? At 0 negative, I am no longer in position 2. I'm in position 1. So at t equals 0 negative, my circuit would look like this. I have a 12 volts. I'm in position 1. I have a 6K. I have 100 microfarad. And I have a 3K. Right? This is a little bit before 0. So we're in position 1. But look what happened If you look at this circuit over here, everything in this circuit is constant. This is constant. This is constant. Therefore, voltage across this capacitor must be constant. What happens to a capacitor with the voltage across it 0? What is current through it? 0. Therefore, this capacitor becomes an open circuit. So my circuit basically looks like this. Right? What I'm claiming is that VC at 0 negative is the same as voltage across this 3K. Right? They're in parallel. So what is voltage across this 3K? That's a voltage divider. So VC 0 negative is 3K divided by 3K plus 6K times 12, which is 4 volts. What does that tell me? It tells me VC at 0 plus is the same as VC at 0 negative, and that's 4 volts. Therefore, K1 plus K2 is 4 volts. But what was K1? We just computed K1, and K1 was 0. Right? Therefore, we know K2 must be 4 volts. And we're done. VC of t is 4 times e to the power of minus 5t for t greater than 0. Right? But that's not what the question is asking. The question is asking, what is this IT? But it's not really difficult because I know voltage across this. And I know voltage across this capacitor is exactly the same as voltage across this 3K. Right? So I can find current through it. So step 4. Solving for I of t. I know I of t is voltage across the capacitor divided by 3K. We know this is voltage across the capacitor, so we're going to plug it in there. So we have 4 e to the power of minus 5t divided by 3K. So it's 4/3 e to the power of minus 5t, basically million. And this is true for time greater than 0. Right? So what we're going to be doing next lecture, we're going to do a couple like more examples on this. Basically, we're going to go through all the steps again and see how we can like solve a circuit with, like, for example, an inductor. I'll see you guys Wednesday.